welcome to Summative Lecture number 2. In this lecture we're going to look at a way to sketch curves using all the calculus that we've learned so far. Just to start though, I want to take a look at a quick graph that I've drawn and answer a few questions about this graph. We want to look at how many points of inflection it might have, areas where it's concave up, concave down, intervals of increase and decrease, look at the asymptotes perhaps. So just informally looking at this, my first part of the graph as I look at it from left to right is increasing into a point right about here where it then starts to decrease, and it continues to decrease forever and ever and ever until it jumps to the other side of the what looks like a vertical asymptote, and then my graph is increasing to this maximum point, and it's decreasing again till about here where it flips from being concave down and looks like it's now concave up, and it looks concave up until about here where it again flips to a concave down section, and this keeps happening as we keep tracing this graph, and then it finally levels off. So if I look at this, I can see 1, 2, 3, 4, 5 points where the graph changes concavity. 5 points of inflection. So if I want to look at areas where it's concave up, well, I can see that here it looks like it's following that concave up pattern. So there's 1. And here it looks concave up. Here it looks concave up. So I think we have 3 sections where this graph is concave up, and 1, 2, 3, 4 sections where the graph is concave down. If I'm looking for intervals of increase, I'm looking for sections where the graph's slope is positive. So it looks like my first section of the graph, the slope is definitely positive even though it's flattening out. So there's 1 section of increase, and then the slope becomes negative. On the other side of the vertical asymptote I have positive slope again, so 2 sections of increase, a little bit here, 3 sections, and then 4 sections of increase. For my intervals of decrease, again, I'm looking for sections where the slope is negative. So I see 1, 2, 3 sections of decrease. And then finally the asymptotes. Well, it's easy to see that I have a vertical asymptote around x equals 0. And it looks like in this graph I have 2 horizontal asymptotes. Horizontal asymptote at y equals 2 and a horizontal asymptote at y equals 1. So that's my horizontal asymptote, that's my vertical asymptote, and that brings me to a point that I want to talk about. We're probably not going to look at it in this video, but it's something that's going to come up. In advanced functions, you were probably taught that graphs, curves will never cross their horizontal asymptote, and that's not technically true. Horizontal asymptotes are different than vertical asymptotes. Horizontal asymptotes pull the curve towards them for very extreme values of x. So locally we can cross over a horizontal asymptote any number of times, but eventually as we get to larger or more positive values of x and more negative values of x, the curve will flatten out and approach the asymptote rather than crossing over it. And we'll look at that in some later examples. So if I think about these 6 questions that I've asked you about this curve, we can use all of this information, all of these 6 questions to sketch a curve, accurately sketch a curve. And that's exactly what we're going to do. So our method, our algorithm for sketching a curve follows these 9 steps. So the first thing we'll do when we're sketching a curve is find any discontinuities or holes or restrictions. Okay, restrictions are things like the square root of a negative value. Next, we'll identify vertical asymptotes, horizontal asymptotes, or oblique asymptotes. Once we've done these 4 things, then we can look at finding the x and the y intercepts. And the first 5 items on my list are done with the original function f of x. After we've done these 5 things, we're going to then take the derivative and locate possible max-min points and our intervals of increase or decrease. So that's done with the derivative, first derivative. Then we're going to take the second derivative and identify any points of inflection and test for concavity. So that's the second derivative. And once we have all these 8 questions answered, we can accurately sketch the curve. So just a few points to remember about this method that we're going to use, and I'm going to do an example in a moment. You often don't need every step. We've looked at many functions that don't have any asymptotes. So when you're following this algorithm, don't often use every step. And the second point to remember, from advanced functions especially, you know the general shape of most of the functions that we're going to be looking at. You saw a lot of functions when you took advanced functions. You've seen more functions from grade 11 math, so you know the shape that most functions should take. So you should get a sense of when you're working and when things are going right and maybe when things are going wrong. So let's take a look at an example. Let's sketch the equation y equals x cubed minus 12x. And I'm going to present my ideal solution and what this should mean to you, especially for the summative. Do this every time. Don't skip steps. So I'm going to sketch this. And I'm going to start by looking at my algorithm, and I'm going to identify any holes or restrictions, and I know this cubic function has no holes. And it has no restrictions. I also know this has no vertical asymptote. This has no horizontal asymptote, and this has no oblique asymptote. So I've knocked off the first 4 items on my algorithm just by realizing and remembering the shape of this function. So next up, I want to identify the y-intercept and the x-intercepts. Y-intercepts happen whenever x is equal to 0. So in my equation, I can sub 0 in for x. And I, of course, get y equals 0. X-intercepts happen whenever y is equal to 0. So I'll make y 0, and I need to solve for x. So I'll do this by factoring. I'll factor out an x from both terms. I end up with x times x squared minus 12, which means that x can equal 0. or x squared minus 12 equals 0, which means that x squared equals 12, or x equals plus or minus the square root of 12. Don't forget the plus or minus. I do want to simplify this radical, and root 12 simplifies to plus or minus 2 root 3. So I can say that the y-intercept is 0, and the x-intercept is 0 and plus or minus 2 root 3. So now that I've identified the intercepts, my next task is to find those intervals of increase and decrease and those possible max-mins. So I'll take the first derivative of this equation and I get 3x squared minus 12. I'm finding the possible max-min points, so I'll set this equal to 0 and solve for x. So I can common factor out a 3 from both terms. And then I have a factor that looks like a difference of squares, so I'll factor that using difference of squares factoring, and I get x plus 2 times x minus 2, which gives me solutions of x equals negative 2 and x equals positive 2, and these are my possible maximum or minimum points. So next I identify the intervals of increase or decrease. So on a number line, and you have to do this, plot your two possible max-min values, 2 and negative 2. And then we'll just pick some values. So I'll pick a value less than negative 2. So I'll pick negative 3, and if I sub negative 3 into my factors, I get a positive times a negative, which is positive overall, which means my function is increasing. If I pick a number like 0, a number between negative 2 and positive 2, and I sub it in, I get a positive times a positive times a negative. I get something that's negative overall. So my function is decreasing between negative 2 and positive 2. And then if I sub in a value greater than 2, like positive 3, I get a positive times a positive times a positive, which is positive overall, which is increasing. So this lets me confirm that I have a max at negative 2 in some point, and I have a minimum at positive 2 in some point. What you need to do is take those two values and sub them back into your original equation and see what y values you get. So you can determine what point those max and mins are at. If I sub negative 2 back into the original, I get a y value of 16. And if I sub positive 2 into the original, I get a y value of negative 16. So last step before I actually sketch this is to find concavity and points of inflection. So I do that by finding my second derivative, which is just 6x. Set this equal to 0 and solve for x, and this is simple. I get a solution of x equals 0. So this is a possible point of inflection. So again, take this to my number line, mark my possible point of inflection on my number line, pick a value less than 0 to sub into my second derivative, so negative 1. 6 times negative 1 is negative, which means between negative infinity and 0 I have a curve that's concave down. If I sub a number greater than 0 into x in the second derivative, I get a positive value, which means I have a curve between 0 and positive infinity that looks concave up. And since concavity is changing over that possible point, that does confirm that I have a point of inflection at 0 and some value. So again, I'll take that x value of 0 back to my original equation, sub it in, and I get a y value of 0. So I need to take all this information, my point of inflection at 0 and 0, my minimum point, my maximum point, my y-intercepts, my x-intercepts, and even where my function's increasing and decreasing and what the concavity looks like. And I'm going to take all this information and I'm going to plot it on an axis and I'm going to graph it. Created my grid here, marked my axes. Sometimes in these questions you need to get creative and stretch your axes or scale them a little bit. And I'm going to start marking in all the critical points that I've identified. So I've identified that I have a y-intercept at 0 and an x-intercept at 0. So I'll mark that point, 0 and 0. I've also identified an x-intercept at 2 root 3. And it's hard to do this super accurately, but about there would be my x-intercept at 2 root 3 and 0. Also an x-intercept at negative 2 root 3 and 0. Also a maximum at negative 2 and 16, and a minimum at positive 2 and 16. And I need to connect all these points. I know something else as well. I know that between negative infinity and 0 on the x-axis, my shape is concave down. So I'll try and do this as smooth as possible. It's difficult on the smartboard program I'm using. But there's a concave down curve. I don't like that. I'm going to fix that. So I'm making this as smooth as possible. There's my concave down curve. Gets to 0 and 0, and I found that 0 and 0 is my point of inflection. And then from 0 to positive infinity, I have this concave up curve that passes through those critical points that I've marked, making it as smooth as possible. I don't like that part at the end either. There we go. So I've sketched my curve. It's gone through all my critical points. The only thing left I need to do is label this curve, and I'll label it as y equals x cubed minus 12x. Okay, so on the summative, you're going to be asked to sketch some curves, and we're going to spend lots of time practicing sketching. If you want to get perfect, if you want to get as many marks as possible, you need to do this method every time. Identify holes, asymptotes, restrictions, find your x and y intercepts, find your intervals of increase and decrease and your max and min values, identify points of inflection and concavity, and then take all the information, mark it as accurately as possible on a graph, mark your scale, x and y axis, sketch the curve as smoothly as possible through those points, and label your curve. If you can do that, you'll get perfect every time. So in class, we're going to spend some more time practicing. I'll do one more example, at least. Give you lots of time to practice different curve sketching. Thanks for watching.